Welcome to video 14. This is our last video of this unit, and it's on using conservation in collisions. So the essential question we're trying to answer today is, how can I use conservation principles to explain and predict the outcome of a collision or explosion? So in previous videos, we've talked about conservation of mass and how mass can't be created or destroyed, but it can move around and we can track it. When objects collide or explode, the mass of each individual object might change, but we know that the total mass of the whole system containing all the objects will not change, and this is due to conservation of mass. For example, if something explodes, all the newly created little pieces will add up to have the same mass as the mass of the original object before it exploded. If things collide together, the total mass of the two objects in the system before the collision will be the same as the total mass of the two objects after they collide. So we tend to think of collisions and explosions as big, dramatic things, but in reality they happen on a small scale every day. Catching a ball, for example, is an example of a collision between your hand and the ball. When you walk and your foot is pushing off and away from the floor, this is an example of a small explosion between your foot and the floor. When objects collide or explode, the velocity and momentum of each object will also change. But conservation of momentum means that the total momentum of the system containing all the objects in that system will not change. So when one object gains momentum, another object must also lose the same amount of momentum. So momentum is conserved. Velocity is definitely not conserved, and we'll talk about that more in the future. So let's make a prediction about what is going to happen in a particular scenario. So we have two ice skaters with the same mass, and they're going to push off of each other. So think about, what do you think is going to happen next? So hopefully you came up with that one of the skaters is going to move forward with a positive velocity, and the other skater is going to be moving in the opposite direction with a negative velocity. So we're going to use conservation of mass and momentum in this problem to figure out why this makes sense. So we first need to start this problem by drawing our before and after systems. Notice the solid line around both the before push-off and after push-off scenarios, indicating that it is a closed system. And in a closed system, both mass and momentum are conserved. So if we looked at the system before the two skaters push off, skater 1 has a momentum of 0 because she's not moving. Skater 2 has a momentum of 0. She's also not moving. And the sum of their momenta also equals 0. Looking at their mass, skater 1 has a mass of m, skater 2 a mass of m, so the total, or the sigma mass for the two skaters, is 2m. Because both mass and momentum are conserved, at every instant in time, the system of objects' total momentum must equal 0 in the future. So if we look at the system after push-off, the total mass is the same as it was before the push-off. The total momentum is the same as it was before the push-off. Well, how can we get a total momentum being 0 after push-off if both those skaters are moving? And the answer is because one of those skaters is moving in the positive direction, so they have a positive momentum, and the other skater is moving in the negative direction, having a negative momentum of the same magnitude. So if you add that positive momentum and the negative momentum, they're going to cancel out to have the same total as we did previously before the push-off. So we want you to be able to explain or predict the results of a collision or explosion. And in order to do this, we're going to give you this tool for tracking mass and momentum in systems called an MVP chart. And in an MVP chart, you first draw the before and after systems. You create a chart underneath the drawing with one column for each object in the picture. MVP stands for mass, velocity, and momentum. You then fill in the values of the variables that you know, and you use equations and conservation principles to calculate more values until you've got the whole table filled out to make your prediction. So now we're going to look at a collision and practice creating an MVP chart so we can predict what's going to happen to our object's mass, velocity, and momentum. So we're going to start by drawing pictures of our systems before and after. In our before picture, we've got a picture of maybe a Mars-sized planet colliding with Earth. In our after diagram, we've got kind of a big mass of the two of them together, stuck together. We draw a MVP chart below our first picture, and as you can see, we make a column for each of the objects that are drawn in the picture below. The third column has the symbol sigma at the top, and that represents where we're going to add up our mass and momentum values. We cannot add our velocity values together. After these two objects collide, we're going to have one big blob that we'll call Mars-Earth, and you can see we just have one column in the MVP table underneath the after picture, representing the one big object that's left over. Our next step is to start filling in the values we know. So we know in this case, we're going to say that our Mars has a mass of 5 kilograms. Earth has mass in this case of 20 kilograms, maybe not super realistic. Mars is coming in with a velocity of positive 10 meters per second, and Earth is coming from the other direction with a negative 20 meters per second velocity. Our next step is to calculate the momentum of Mars and the momentum of Earth. And to do this, we need to use the equation P, which is momentum, equals mass times velocity. We're going to plug in our values. So we have a mass of 5 for Mars. We have a positive 10 meters per second velocity for Mars. And as we multiply those together, we're going to get a momentum of 50 kilogram meters per second. So we're going to put that in our chart. Note that it's positive, so our momentum of Mars is positive. For Earth, we're going to do the same thing. So we're going to use the same equation to calculate momentum. We are going to multiply the 20 kilograms for the mass times the negative 20 velocity, meters per second velocity. And we solve this to come up with a negative 400 kilograms meters per second, and we're going to put that in our chart as well. Now we can see that the total mass for every object in our system comes out to 25 kilograms. Additionally, our total momentum for every object in our system comes out to negative 350 kilogram meters per second. So we filled out the chart with the values that we knew. We also calculated momentum values, and we summed up the total mass for the before system and the total momentum for the before system. So now we can use a couple rules in order to figure out what the values are going to be on the other side, so in our after example. So the first rule is that we know that mass is conserved. Okay, so we know that the sum of all the mass on one side has to equal the sum of the mass on the other side. Mass is conserved. We also know that momentum is conserved. So the momentum in the before scenario has to equal the momentum in the after scenario. This is a closed system. Nothing has left the system. So if the mass hasn't changed of the whole system, and now we have one object instead of two, this means that Mars Earth's mass must be 25 kilograms because there's only one thing in there now. The same can be said for momentum. So since momentum was conserved, there's only one object inside, the momentum of that object, the Mars Earth, must be negative 350 kilogram meters per second. So the variable that is not conserved here is velocity. So we can't just add up our velocity values and plop them in on the Mars Earth side. So what we have to do instead is we have to solve for the velocity of Mars Earth. So we're going to take our same formula that we used before, and we're going to put in values for momentum, which is the negative 350, and the mass, which is the 25, and we'll put in a v for velocity because that's what we're trying to solve for. We want that v to be all by itself on one side of the equation, so we're going to divide both sides by 25. So here we can cross those guys out. We're left with v on one side, and on the left we can divide negative 350 by 25, and we get negative 14 meters per second for our velocity. And we're going to put that into the chart as well. So we now have two complete MVP charts. We have kept track of all our mass from before collision to after collision. We've kept track of our momentum of both objects. The total momentum before the collision is the same as after the collision, so both mass and momentum have been conserved. And we've gone and solved for the velocity of Mars Earth afterwards. And notice that it does not add up. Velocity is not conserved in this case, or ever. So now use this space to summarize your notes. Let's go back and look at our essential question, which was, how can I use conservation principles to explain and predict the outcome of a collision or explosion? So write a few sentences summing up how mass and momentum are conserved in collisions and explosions in closed systems.